Hi, everybody. Happy Friday. This is Jon with Radenso, and we've also got Rob here, our lead DSP engineer.
Hey, guys.
And we wanted to kind of get back to producing these videos. We're still operating in a very limited standard. Actually, we're the only people in the office today. But given that things have kind of slowed down a little bit due to the pandemic, we thought it would be a good opportunity to maybe take a little bit of a more technical dive into a pretty important fundamental topic for radar detectors, and that's DSP, or digital signal processing. And I mean, the concept of DSP is something that's in all around you.
Yeah, it's everywhere. Literally
every possible industry. But I kind of think it's funny that in the radar detector industry, we might use that term a little bit differently than in any other engineering capacity, because it's kind of been a marketing thing.
Sure, and it's been that way for every other industry, from car audio to cell phones to
image editing.
Yeah, you bet.
Photoshop.
Everything's DSP, but it's what we're doing is just our variety DSP for a specific application, and we're using a subset of DSP to do the things that we need to do to have a great detector.
Yeah, so it's interesting. I asked on RD Forum what questions you guys had around DSP, and you guys responded with some really, really great stuff, and I kind of broke it down into 3 separate categories of what the questions were. The first one was basic DSP questions, kind of what is DSP, right? We don't know anything about it. Let's talk about defining that term. The next category was, well, okay, now we know what it is, but how does it help me? What does it mean for my radar detector? And that's kind of more like the manipulation of this digital signal.
Right.
And I think that's going to be a second video that we're going to do. We're going to do a 3-part video series just on DSP. And then the third one is probably going to be the most technical, which is like hardware-related questions, FPGA versus Blackfin.
Sure.
Some of the more technical users on RD Forum asked really good questions about that. So you guys can look forward to a 3-part series just on DSP. And this first video today is going to be a little bit more basic, but focusing on general concepts so people can understand.
Sure.
So I guess in the general concept, what is DSP? What is digital signal processing?
Well, I think the first thing you have to answer is what is a digital signal, right? What are you processing that is a digital signal, and how is that something that we can interact with digitally? So if we think about a signal like this red trace here, a signal is inherently an analog or a continuous amount of energy that we're measuring. So with the normal
so a signal
waveform,
is just energy.
Yeah, I mean, yeah, it's a signal is just information, right? And so when we talk about a signal, we're talking about, the magnitude, the amplitude of a waveform, an RF wave, right? So what we want to do is we want to process this. We want to look at this waveform and analyze it to see if there's somebody shooting us with a police radar.
Do we care about that or not, right? That's a fundamental question.
And to do so, we want to look at this signal, but we want to look at it in a digital system. But a digital system doesn't understand a continuous range. It needs to be quantized. And what that means is to take a continuous analog waveform and to measure it, and it's called to quantize it and put it in discrete steps. And that's what this blue trace is.
And that's just a fundamental inherent difference between a digital system and an analog system, what you just described. That's kind of the essence of the difference between them at the most basic level, right? It's ones and zeros, which is not a continuous waveform.
It's a discrete quantity.
Yeah.
So you have discrete values at discrete points in time. So we call those points in time samples. So every sample period, we look at the value of this waveform and we assign it a number. These different values. And so instead of being any number of values between, say, -1 volt and 1 volt, we might want to say we're going to make it some known value between, for instance, -8192 and 8191. Now, every point in time, this signal has an instantaneous value associated with it, and now we can bring that into the domain of digital processing. We have numbers that can be interpreted by our FPGA that we can run mathematical operations on, but the prerequisite to that is to quantize this and turn a analog signal into a digital signal that we can process.
So in the radar detector industry, people talk about digital radar detectors versus analog radar detectors or detectors that have DSP. And I think that that's actually, it's a little bit of a, I don't want to say an incorrect use of the term, but to be perfectly clear, every radar detector in existence, even analog designs like our Radenso Pro-M, have analog components to them and digital components to them. There is digital signal processing that's done in every radar detector, but saying that something has DSP, it's kind of like saying cars have wheels. Like, there's different size wheels. There's wheels that are useless on your car, right? Like, it's when the radar detector community uses the term DSP, they're not really talking about the very limited signal processing that's done on like a Radenso Pro-M.
Right, right. You can do DSP in any number of places in a design with any amount of utility, and the extent to which you are leveraging DSP to accomplish a detection has a lot to do with it. So you could quantize a signal and just, do some very basic operations at some very limited part of your system, and you have a DSP.
And
right?
that's the way that most analog detectors work. I mean, by the time there is a rudimentary processor in almost every radar detector that is looking at a signal and saying alert or don't alert.
Right.
And if you're really stretching it, you could say that's DSP.
Well,
but
if you really want to stretch it, you could look at an LED that represents a signal threshold. If that LED is on, it's a 1. If it's off, it's 0.
Yeah,
then an LED
DSP.
is a 1-bit DSP, right? So, it's pretty easy to take advantage of that terminology.
And that kind of might relate to another question that somebody had. I think it was actually Vortex that said he's seen detectors from the 80s that advertise DSP, and what's different today? And that's kind of what we're talking about, where detectors in the 80s, I guess they did have DSP, but they didn't have DSP in the way that a modern, for example, a Redline 360C or Theia or something like that is doing, or the R7 is doing DSP. They didn't even have that hardware available. So
well, that's like saying
it's almost like it's like, I don't know, like...
It's like saying the Apollo spacecraft had a computer. It wouldn't fit in this room.
Exactly.
But it was still a computer. Your smartphone has hundreds of thousands of times the processing power. So yeah, it's always existed in the fact that a digital signal being processed is really just arithmetic. So I don't think we've changed that. But it's the extent to which things we can do in DSP, how quickly, and for what price to make it a reasonable choice.
So when people say digital detectors nowadays, I think what they're really referring to is a radar detector architecture that digitizes the signal as soon as possible.
Correct.
And that's more along the lines of like modern detectors that just take a down converter and then digitize it as soon as possible.
Right, and that's basically the objective. The sooner you can digitize a signal, the sooner you can start doing interesting things to it. An ideal radar detector would be a feed horn plugged directly into an analog digital converter. Unfortunately, we still have to do a little bit of analog stuff first, but in our design, we do very little analog work before we bring it into the digital domain and start doing DSP against it.
So one of the big questions that people have is, okay, cool, you do DSP in your radar detector. Why? What's the point? Does that make it better? Does having a detector that does DSP, is that automatically better than every detector that doesn't? And related to the diagram Rob drew, not necessarily, because all that a digital detector is, if you don't do any software development, is just a digital representation of an analog waveform. So it's kind of like what you do with the DSP matters a lot more than just looking at something digitally.
Well,
is that correct?
Yeah, it's worth noting that as soon as you quantize the signal, you've lost a tremendous amount of information. And so doing this effectively and knowing why you're doing that is really important, because as soon as you quantize a signal, as soon as you say this continuous analog quantity is this value, this value, this value, you are losing information you never get back. So you have to be, first of all, very careful about the integrity of the signal before you digitize it. And when you digitize it, you never get that information that you've lost back. So you have to use it pretty effectively.
And that's why stuff that we've talked about in our other videos, like spending a lot of money on a good analog to digital converter, is so important. You want to maintain as much of that resolution as you can.
With a better ADC, these steps can be much smaller, where you have a wider range of these values that can represent this continuous waveform.
Yep. So now that our detector, or any detector that's digital, let's say that we've digitized the signal, what now? What is the rationale for even wanting to look at a signal digitally instead of an analog? Because you did just say that if you're not careful, you might actually lose a little bit of resolution. So why would we want to take that risk? What's the upshot?
Well, the benefit is that once that signal is digital, we can manipulate it however we want in any number of different paths through any number of reconfigurable circuits and look at different aspects of that signal. We can look at it through several different filters at once. Basically, what it allows us to do when this signal has been digitized is to basically synthesize these huge RF networks that you normally find on a radar detector, an analog detector. But with an FPGA, we can basically put this through any arbitrary kind of processor or circuit that we want to, and we can redefine that circuit at will. Really, once this is digitized, we look at it with software, but the software is changeable at runtime. So basically the networks, the RF components that you normally have, we get to define in software. It's a software-defined radio.
So it sounds like flexibility is one really big advantage for doing things digitally. If you find a better way to do something, you could just do it. Or in our case specifically, I think what is kind of an interesting analogy is to talk about DSP as it relates to like image processing.
Right.
Like if you guys have ever used Photoshop and you take a picture, you can edit that picture in a lot of different ways. And Rob used the word filter. You can apply filters to Instagram pictures. That's DSP. That's the advantage of DSP, I should say, where you have this starting signal, and if you think it's too dark, maybe you're having trouble making out details in the shadows, you can drag a slider and edit that image after you've obtained it. Right. Now, if you compare that flexibility to developing photographs in a dark room, once that image is developed, if you don't like it, you're kind of out of luck, right? And with using effective DSP, we retain all of the integrity of that original digitized signal. So you can even look at things 10 different ways without damaging the original.
To continue with that analogy, it's like looking at a digital camera as well. The sensor on a digital camera is an analog to digital converter, and the lens is basically the RF front end.
Mm-hmm. So if the lens is the horn.
Right.
Yeah.
So if you put good money into that apparatus and you have a good sensor, then you can do an incredible amount of manipulation on that image without losing resolution. That's exactly what we're trying to do.
Yeah, and it's pretty interesting because people ask sometimes with Theia, well, if you're using AI, why do you need DSP? And it's important to understand that the DSP is before the AI. We're literally trying to draw a picture, for lack of a better term, for the AI to say, right, hey, that's a mesh diffusion, that's a BSM. But if you give the AI a bunch of black blanks pictures, it's not going to be able to tell a difference.
Right.
So the goal of our DSP is to draw the most ideal picture possible for the AI or for a match filter or for whatever we're trying to do. And that's tremendously powerful because whatever feature that the AI hones in on, let's just say that the AI determines that bandwidth is what it likes. Rob can write DSP to effectively, just like you increase the shadows in Photoshop, we can increase how the AI sees bandwidth.
Once we isolate some phenomena of the signal that the AI is really good at using as some primer for making an AI selection of a signal, some sort of a successful classification, we can take our DSP and reconfigure it to enhance whatever subset of that signal metric that AI is doing a good job inferencing on.
Yeah, it's really pretty wild stuff. And one question that somebody asked, which I think is a clever one, is are there problems that you can solve with DSP that are unsolvable or can only be poorly addressed in analog?
It's a great question. So the answer is yes. There's plenty of things you can do with DSP that are very hard to manage in the analog domain. One example is filtering, right? If you want to select a part of a signal to do analysis on and you want to filter out something you don't want to see, I mean, imagine looking at a BSM that's transmitting and you want to look at a CW wave. Well, you might want to just do a bandpass filter to look at one part of the spectrum. You want to look at one wave and you don't want to look at anything else.
So you're talking about doing this like on the fly.
Correct. But then that's the problem, is that you can build great filters out of analog components, but you build a specific filter with specific analog components like resistors and capacitors and inductors. With a digital filter in the FPGA, it's very equivalent to the same kind of filter, but you can change the values. You can change the frequency you're looking at, the bandwidth you're looking at it, the amount of gain that it has, and you can do so many thousands of times a second, and we do that. So it lets you basically take these same strategies and make them dynamic and reconfigurable, but they're also so much better filters than you could ever really fit on a board like that. You would have to have a tremendous large size board with incredibly complex components to make the same kind of filters that we can make just with our digital signal processing. And another one of the big advantages is repeatability. When you have very big complex systems and very tight filters, this is how you start getting hot and cold detectors. You have parts that aren't exactly the same. You have things that can be matched by hand. You have all these variables, and you can automatically compensate for that in DSP. So much smaller footprint size, less complexity, more repeatability, more stability.
Well, it's interesting too, just to throw out another point, is that when you do something in analog, like just a filter, to stay with that, it's kind of like a one shot and done, but when you do it digitally, especially in an FPGA, we can add the power of context and even have stuff like selectable filters.
Sure.
Like we can, and I'm making this example up, but we can literally say if you see a signal that is 200 megahertz wide, we think it's probably going to be, I don't know, a Ford BSM, select a specific filter that enhances a specific portion of that signal,
Sure.
and then send that to the AI.
And that's called a match filter.
You could never ever do that. Well, I mean, you could do it in analog, but as you said, it'd be huge, and then you...
Well, look at the Valentine one. That is basically the whole front end of that thing is supporting a hardware SAW, DDL, which is like a match filter, right? So, but if we want to do that, we load a DDL.
Yeah,
or
exactly.
we load, you can take the same hardware and make it do whatever you want, and you can change it as often as you want for free.
Yeah, it's really wild stuff. Probably two more questions. One was, can different detectors / companies all use DSP and do very different things with it? And I think obviously the answer to that, as we've explained, is yes.
Right.
And the constraints to how each company does their DSP is going to be probably a lot of the time driven by the hardware design. Like if the Valentine one uses DSP, it's going to be a very different type of DSP than we would use because the hardware on the analog side feeds it a different, I don't know how to describe it. It feeds it a different...
You have an architecture that is built to do a specific thing a specific way, and your DSP is part of the implementation.
Exactly.
And
that's what I was trying to
where
say.
and when you use DSP is going to depend on a lot of things. Is it compatible with the cost of the product you're trying to make? Do you have the talent in-house to work on the specific hardware you want to work on? What's your timeline look like? It's very difficult to...
using DSP in a design is kind of like choosing the right type of paint for like a toy model or something.
Right.
Like it has to be very specific and intelligently designed.
Right.
To
You
be
have to know
effective.
exactly what your goal is because there's so many options for using it and buying the parts that allow you to use it that it's very difficult to guess at. You have to know specifically what you want to do and why and how good it has to be before you ever get started.
In that same vein, looking at here and like for where we are today, where we're starting to see stuff like software-defined radios and relatively inexpensive FPGAs relative to what they were 15 years ago.
Oh, sure.
Where do we go from here DSP-wise? What do you see like the next decade kind of with radar detectors? Like, is this like a processing power kind of a revolution? Are we going to have more complex algorithms that we can use? Like, what do you see as the future?
Well, I think that, with everything being constrained for size, weight, and power, it's called swap constrained, we see new chips that are getting cheaper, smaller, they run with less power, and they have way more speed and complexity. And that being the case, we talked about the ideal detector basically having an antenna going right into an ADC, but we're getting there that way really quickly. There's devices that are coming out that are FPGAs with software-defined radios, 8 of them built right on the die.
That's
that
crazy.
plug directly into an RF input. And so as that stuff gets smaller and more power efficient and less costly, I think that it's going to be very hard to justify not doing things with DSP.
So I guess you see from the performance side of things, inching ever closer to the more ideal the theoretical maximum performance, right. But then also being able to run more simultaneous algorithms, sure. Faster algorithms, using stuff like bigger FPGAs that gets cheaper, and
right.
So kind of just heading in the same direction, but better and better and better.
Better and better, cheaper and cheaper, more accessible.
Smaller.
As this becomes more popular, more and more people are going to have that skill set to kind of do this stuff. It's going to be a lot more accessible for people, and I think I'd like to see it get to the point where it's accessible enough that it can basically be a hobbyist level thing. And at the kind of complexity we're working with, it's very difficult to do that. So
for sure.
We'd like to see that kind of open up a little bit where everybody can, play with an algorithm.
Yeah, it's pretty cool stuff. So I think that's pretty much all the questions for today's video. I think next week we're probably going to talk about a little bit more in detail about specific algorithms and how we solve specific problems with DSPs. So that should be a fun video as well. Maybe we'll get some visual examples of actual signals to look at for you guys. But until then, I really appreciate you guys tuning in. Don't forget to like and subscribe to our channel and enable notifications if you haven't done it already. And we wish everybody the best and for everybody to stay safe and healthy until next time.
Take care, guys.
Thanks, guys.